Hello. Okay, so we are back. I'm afraid I cannot be. Yes, just in time. Good morning. I'm afraid I cannot be connected directly to the screen, but everybody has a computer, so let me come back to the original presentation that I sent to you last week. Okay, anyway, this is being recorded. So now I'm going to page number 12. Okay, we finish, admit. Good morning, Hernan. Good morning, can you hear us? Good morning. Hernan, can you hear us? Hernan? If you can hear us, please say something. Okay, meanwhile you're sitting up. Also, you're connected there? Very good, thank you. So, thank you for that. So, whatever person is connected, you are co-host, Mugi, just accept it. So, this example, I'm in the page number 12 with the zinc extraction. Remember, this is a recycling plant, meaning it takes whatever iron-based material like cars, refrigerators, whatever that contains iron, and then this is first it's molten with an electrical arc, and during this process, droplets, very tiny droplets, I'm talking about 0.5 microns, 0.2 microns, like an aerosol of molten, very hot liquid, it's generated as a residual. This molten dust, which is a residual, goes to scrubbers, which is an equipment when you put in contact with water, and it generates a dust, very fine dust, and this dust contains 40-45% zinc, which is a material that we want to recover. It contains a lot of zinc, but also contains cadmium and lead. Okay. So in the case 3 that I sent it to you today morning with a translated version for the diagrams, it's explained in more detail, 50 pages, how we did the engineering, meaning characterizing the material. First step is characterizing the material, always. What do we have as a feed? XRD, XRF, XRD minerals is very important for us in order to understand what type of dissolution process, meaning leaching, we want to do, in order to know what are the pH or RP conditions, and then we come back to these Courbet diagrams. Okay? And then in between, we can do whatever we want as a process engineers, and page 12, whatever we want. But before going to the process design or the decision, we call it the root path or the process path, we need to seek what type of product can we have. It can be, in this case, it can be pure metal, that means electrowinning. It can be sulfate, for example, zinc sulfate, chloride. So that depends on the market. So always need to see what are the possible products and determine the size of the market, the trend of the price. Both extremes. So the characterization of the raw material that you have, and then the product that you can achieve. That is the slide that I'm showing there. When you have different products, we don't know yet. We have a gross idea what are the processes: hydrometallurgy, pyrometallurgy. In both cases, we also need to liberate, but in this case, it's a verified. Always on top of that, what are the environmental restrictions? So this is an environmental problem because we have a residual that today is a problem because it contains lead and cadmium, and this is disposed as a toxic material. It has a cost. So you already know how much is the baseline of the cost. Okay? So whatever treatment that you do, reducing the mass, let's say you have a process which is 50% efficient, you already know that you're reducing 50% of the mass. Okay? So you don't need to have 95% efficient process. You need to have all the variables, economic and environmental. If you just want to stabilize and remove cadmium and lead and cadmium, it's also an alternative. Perhaps you just can remove cadmium and then you change the toxicity level of the residue. Okay? So in this case, we explore different products, and then in the next page, page 13, we have narrowed down the technologies. The technology is not that difficult in terms, in general, we work with solids, solutions, or well, listen up, when we start with solid, we end up with a solution after leaching. From solid to leaching, as a process, it can be atmospheric leaching, or it could be an autoclave leaching in case the kinetic is too slow. We need to do a very high temperature, 200, 300. But in any case, from solid we go to liquid. And then in this liquid we have a soup, plenty of different ions. And depending on the concentration of the ions, if the concentration is low, we don't even think, you go through an ionic exchange. If the concentration is in between grams per liter, we can think in solvent extraction. If the concentration is really high, 300, 400 grams per liter, it can be either direct electrowinning, or it can be precipitation, crystallization, and then you purify the content. In order to decide what of the line that you want to do, you need to have the specifications of the product that you want to have. If you want to have zinc sulfate, it requires a specific condition to be used as a fertilizer. For example, the amount of chromium, the amount of lead. So again, regulation for the product. So in the PowerPoint that I sent today morning, case 3, you have 50 pages with all the analysis, economical analysis, the products, and then it has an experimental design for, we call it readiness level 3. Do you know what is TRL? TRL stands for technology readiness level. Whatever application we do, whatever technology we do, we need to refer to this classification that starts from 1 to 9. This was developed by NASA a long time ago to determine if they have a technology, an airplane, aerospace. So 1, it will be, we call it napkin, an idea, conceptual idea, a paper, is a theory, and you end up with an actual commercial airplane. So moving this for mineral processing or process engineering in general is kind of different. Okay? So when we apply a project, when there are funding, or when you have a patent, you need to determine what is your TRL, technology readiness level. You can browse that. I think I'm talking about that in some of the topics, but it's important you to know this nomenclature. In innovation, in applications, You need to know what it means. I'm going to be very brief on that. So 1 means you have a paper, you have calculations, okay, for process engineering. 2 means you have a bench scale, very small one, let's say a leaching process in a 100 centimeter solution with 2% solid. 2% solid is very dilute, it's not for commercial purpose, but it lets you know what are the conditions, pH, oxidant level. You need it to explore if it's feasible to dissolve the product, and you do it with 2% to avoid any mass transfer problem, to avoid any mixing problem. This is TRL 2. Let's say in a small beaker, 2% solid, 3% solid, very small scale. And then you go to readiness level 3. Usually you do that in real conditions. In level 2, you do it with ideal solution. You prepare a solution with distilled water, just change it, because you know all the ions. You have the minimum amount of ions. Okay? In readiness level 3, it's just closer to having. Sorry, even in 2, you can have synthetic material. You can make a mixture of zinc with other elements, you know, just the salt, just to see what happens. 3, it's more real condition. You have an actual powder, real powder, and you have the actual processed water. You know what I mean? Because you have a soup with more ions. But still, level 3 will be bigger level. And then when we are in level 4, it's a larger process. It can be 5 liters, 10 liters, still bench, not more 2%, now 10%. We are exploring the effect of solid content, volumetric solid content. We are exploring more realistic conditions, but still it's bench scale. It's not lab scale, it's bench scale. Imagine 5-liter reactor. Imagine a continuous equipment, let's say 2 liters per minute with a peristaltic pump, you know. It's not pilot, but still better than, not better, higher complexity than a lab scale. Then readiness level, very clear. Usually universities end up with level 4 of the experiment, level 4, 3 and 4. And you have grants for this specific application. But there are some grants that they want you to have proof of concept, you have readiness level 4 to apply to update the readiness level. 5 already means a pilot unit, 30 liters per minute, okay? But it depends. For example, now for the technology that we have developed here, using air bubbles to increase the evaporation rate. I'm not sure if I talk about that, but this technology allows you to increase the evaporation rate from 8 liters per square meter per day to 80. And this technology, the company Enamet, the French company Enamet, want to have the exclusive rights for the technology that we develop here. So for them, readiness level 5 means, I forgot exactly. Sorry? The pilot for them. For me, pilot would be 30 liters per minute. It will be a unit that you can put on a 3/4 truck. With a crane, you can put the truck. Let's say container size. That would be something like that. But in this case, if I remember correctly, I think it's 100 liters per minute for them. They asked me. Okay. So that would be pilot. Readiness level 6 is larger pilot, but running in the plant, running in the facility. Okay. 7 is closer to market, using industrial component, is automated. Readiness level 6 is the industrial prototype, industrial facilities prototype. This is the commercial prototype, and then you improve it, and then you have the industrial version. And when you have 9, it's already commercial. It's commercialized. This notebook is already readiness level 9. It's the commercial product. Understand? Okay. There is another concept. Sorry if I make a detour for that. It's just to understand that you have different levels. So development technology has this path, and then I will not talk more on that. There is something else that is called SRL, System Readiness Level. For example, today we do have the glass bubble technology, which is to recover fine particles, licensed to the company Matheson. They have it's licensed to Matheson, technology developed at Santa Maria. This is readiness level 4. We develop readiness level 4. What is doing Matheson? Readiness level 5, meaning that you test on batch stage rotation different minerals from different plants. You're testing everything. Okay? We are here. When we talk about system readiness level, it's what happens if you put the product in a plant. So if we have this functionalized glass bubble, which acts as a fluffer, it will have an impact if you recirculate the water in a plant. What happened in the filtering stage? What happened in thickeners? We don't know. It's when you integrate a technology into a system, into the whole plant. Having only this, you have no idea what is going to happen in the plant. Then you have another 9 level for system readiness level. Okay? This is enough, understanding that. So in this project, the technology is readiness level 3. Very small, you will see, experiment, you will see here. But it's enough to see the feasibility with a 50-60% uncertainty. Let's say 3 is just to get the proof of concept. Proof of concept, okay? Now, if you go to page 14, it's just to emphasize that, again, we start with raw material, we have a process in between, we already more or less know the path, and then the final use. The final use will be for fertilizer, you know the impact. Why is it important to know that? Because you can determine what is the economical benefit, what is the environmental benefit. You need to characterize that with the KPI. KPI will be the second lecture, how to determine KPI. And the KPI is not for a specific audience. You can have KPI for Greenpeace, KPI for political or policies, you have KPI for investors, you know. So it depends. I'll show you the case of when we use recycled Tetra Pak, because it has impact on society, people, poor people. We will learn how to determine KPI. Perhaps you already know, but the basic KPI always would be kilograms of water or liter of water per ton of material that you process. It's called the water footprint. CO2, kilowatt hour, how many kilograms of reagents do you need, labor. These numbers are important to determine at the end the cost of the product. You need to do all this stuff. So in this example, the whole project is already done. You will see even the economical evaluation. So the assignment will be same thing, but with different product. The product will be flue dust from copper smelter. Okay. If you review literature, if you review papers on the copper smelter, all the focuses are on contaminants. Lead, cadmium, there's very little literature on elements that we can recover. But I do know from colleagues that have been working in 2 gigawatt for a long time ago, they did experiments in secret. They have germanium, they have neodymium, and also, don't remember the one that is being used for IR vision, for infrared vision, rhenium, used for infrared vision, okay? So I will focus on those elements, okay? The challenge of working with very fine particles is mixing. We cannot put that on an aggregate mixer, which is the standard one. We need to think about it, okay? I want to skip this part. This is the kinetic test. We will have a specific training in how to feed data. This is not the right way. Yes?
So the problem is still lost in the observation.
Yes.
You mentioned about the germanium or
Yes.
elements, which are very fine, and you couldn't improve the vegetation.
Yes.
And presently, they're doing
Nothing. Just they are doing the only thing they are doing after you have the electrostatic precipitator, those dust contain a lot of arsenic. Some of them it's leach and stabilized as a not stable component, not solid, but some of them goes to Acuna-Pérez with huge reactor. We will visit those huge reactors, and the reactor is 10% solid, which is very unique. You usually don't work for leaching process of solid. You work 40%, 30%, 40% gold. This is the usual range in order to have a feasible case. Otherwise, the reactor is too big. What happened in the case of Acuna-Pérez? Those three reactors, which is 1,000 cubic meters, very big. The impeller is about 8 meters in diameter. It's gigantic, very big. That was developed originally for bioleaching. It was a joint venture between PHP, huge gigantic mining company, and Codelco, huge gigantic company. They have a joint venture. They look for bioleaching, big project, a lot of money. What happened with this big reactor? The shear stress of the impeller, the agitation, the velocity, killed the bacteria. So they are too fragile that they couldn't make. So they say they abandon the project and they end up with this huge reactor. So the reactor has zero cost for a project. Otherwise, you will not pay the project. Understand? Okay. So the problem with fine particles is not solved. We have some ideas, but I don't want to tell you because it's part of the development. Because I want you to understand a little bit more the limitation that you have with rheology, understand what happened with the curve, shear stress, shear rate, so you will conclude. I'm telling you, an agitated tank reactor will not work. Okay? But this is part of research. When you review the papers, it's also, I didn't mention, it's good to review papers and patents. Patents, in my opinion, is a better source of technologies. Because in the patent, those who have reference to other patents and other papers, but now you can classify. You can have a paper even with readiness level 1. You can have an invention. It doesn't mean that it's ready. You know? Most of our patents is 4 or 5. Now we have a commercial one. It's commercialized. It's the gas sensor, gas velocity sensor. It's commercialized. It's been sold to PHP. So we recover all the levels. Okay. So I'm talking about now slide 31. Slide 31. This plot, slide 31, this plot is not good. You need to have the dots experiment, and then fit the model with more data. We will work on that in a different module. And then you will put the confidence interval, the one that is talking Professor Berg, which depends on the number of points, in order to have technical representation of information, okay, in order to be reliable in terms of confidence interval and all that stuff. It's not that difficult. You will do it both Excel and MATLAB, and also in September the 5th for the third course, I'll be doing a lecture, an online lecture on MATLAB tools. I'm talking about this. Yes, tools, because it's needed. Okay. I'm going to skip all this. You will need to have the block diagram all the time. Block diagram to understand the operation. You don't need to do. I'm talking about slide 34. These are block diagrams because you are setting the operation, filtering the one Sarah was talking about. You remove some of the elements before precipitation. You are purifying the elements, and finally, you will end up with the flow diagram, page 35. When you're saying it would be an agitator reactor, it would be solvent extraction unit, and then you can determine the equipment cost. You don't need to determine all the costs. You don't need to go to the pump level. Because remember, depending on the readiness level, you have 40–50% uncertainty. Just here you have 10%. So when you put numbers, put calculation, don't put decimal, don't put dollars, put thousands of dollars. I mean, it's ridiculous. You see 5.63, no, it's not correct. Just round numbers. And the most important is the most important equipment, let's say the autoclave, and the largest equipment, let's say a sack mill, for example, or primary crusher. Primary crusher is the largest one, the more important, because it requires 2–3 years to build a big primary crusher, for example, and then from there you calculate the rest of the equipment. Usually the most important one, it will be 3 times the rest of the things as an equipment, and then another 3 times facility, depending on the type of facility. If it's pharmaceutical, it will be 5 times because it requires better facilities. Okay, but those numbers are in an economical evaluation. You will find them. Okay? So we're not looking for precision, just to understand what it means, all the steps. Okay, but the important thing is to understand this diagram. Whatever thing you do, I mean, as a checklist, it's all the things that you are putting in your system must go in another place. You cannot have residual streams. All of them must be treated, recirculated. And remember, this is not part of the course, but in the process design we talk about recycling. When you are recycling, you are not removing the ions, you will generate a big problem. That's the problem that we have in flotation process now, because you accumulate ions. You're not removing the ions. So most of the problem that we see in selectivity in flotation today in the world, it's because you don't take care of the ions accumulated by years in the process. You don't have fresh water. Remember, you recycle a lot, especially now, we have restriction for water. So this is very good for us. Okay, now I'm going to slide 36. You will see the Boliden technology. I'm changing the topic, and now I'm talking about concentrates that contain arsenic. In the world, all the regulations require higher standard of arsenic, meaning today we cannot sell concentrates that has more than 0.4% arsenic. Means you cannot sell. In the past, you pay a penalty, so nothing happened, but now regulation, you cannot sell it. Okay? So in the case of Chilean concentrate, specifically Chuquicamata, it contains a lot of arsenic, which is, I'm pretty sure different countries happen like that. So the alternative was roasting. Whatever technology that goes to roasting, pyrometallurgical process that generate gases is going to be really, really complex. It's difficult to control gases through dust in general, electroscopic precipitation. You will have particles going around. Okay? So in this case, Boliden, which is a Swedish company, has this big roaster. It was commercialized by Autotech, now it's installed in Chile, but it's a really, really, really bad. Just to remove part of the arsenic, they generate as a product arsenic trioxide, and then this is stabilized as a, don't remember the compound, but it's not escalodite, which is not stable. Exactly. I understand that, yes. It's not stable. You leach, and then you add lime, and then you generate an unstable, it's not legal. Okay. I mean, it's not stable. So the problem was not solved. So a number of years ago, I think it was about 10 years ago, we developed a technology, just understand that, to convert energite, which is the main, you have energite and energite is in the slide 36, and tenantite, energite and tenantite. You are working with that, yes. Energite and tenantite. That's the one I'm working with. And also you work with that. Energite and tenantite, it can be converted in a process that is called hydrothermal reaction, which is a reaction in a solution at high temperature, 250, 300 degrees. And in order to happen that and avoid evaporation of the water, it works at very high pressure, talking about 20 bars, which is a lot of pressure. 20 bars is equivalent to going deep in the sea, 200 meters. 10 meters is 1 bar. Okay? You have the. So at the beginning, we work with pure energite crystal, go to the reaction, diffraction to see what happened, how it was converted. You have all this data. I'm not sure if you have the data, but it was converted. So that was readiness level 3. Okay, and then we run concentrate from a mineral plant, Coyahuasi. That is readiness level 4. We call it real environment, that in that case was real material. But still, it was in a 1 liter reactor. Still, it was 4% solids. Because you are exploring. See what happens. But at the end, we end up with those, we're talking about these plots. So each individual plot, it was a single experiment when we test at different temperature. Running with autoclaves has the difficulty, and we can review papers on that. And most of the outputs, when you see the kinetic data, they do it like that. Let's say you start at 40% extraction, and they show the plot, I'm not kidding, something like that, to avoid showing that it doesn't start from 0. Come on, what happened? So they lie. No, I'm not kidding. You review autoclave reactors, you will see very often they don't start from 0, and that happens because when you put all the sample, it's a batch test, you start heating up the sample, and then when you reach the temperature 200 degrees, okay, that will be my initial time 0. But the reaction started a long time ago. As soon as you put the reaction, you have a heating curve that take into consideration. You work with that to correct that. It's not a big problem. We use the Arrhenius equation. Okay? So I'm just showing that because to understand that it's very important to understand what are we doing with the data. And you will see very often this type of mistake because people do not understand what is it. Okay. So in this case, we reach up to 95, I don't know, 95, 99% recovery. More important, this is a big criteria. Listen up here. Yes. When you have in the range 60, 90 minutes, 1 hour, 2 hours, it's feasible as a reactor. It's a common value. It's long. It's not as long as days for biological reactors, wastewater treatment, days is usual, But for pyro-hydrometallurgical reactor, we are expecting 1-2 hours. In order to see this equipment, it's 1,000 cubic meter, 60 cubic meter, something real. So if you see a leaching process, which is 120 hours, I've seen colleagues from Chile, professors, showing that. So it's very simple to determine that. Because 120 hours means you have very big reactor, which is not possible. Okay? So in this case, we are able to have a kinetic. Then, of course, you have the trade-off size of the reactor and temperature. It's not the same working at 200 than 300. You have material issue, working at high pressure. But now the technology, the Japanese company, of course, all today sharing in Canada, the three major companies, they are producing very big output there. Big, I mean, 1,000 cubic meters. It's like a building. It's very impressive. Okay, so just to make a comment that sometimes when you have a solution, it's more political because if you ask me, having a rotor is really, really bad. And again, it was developed by a very developed country, Sweden and Finland. But the solution is bad. Okay? In Chile, we develop something more environmentally friendly because it's island. So to finish up that, it's important to understand this is not easy. It requires different times. When you start with technology, going different levels from the idea, because you need to have budget, you need to scale it up. We end up with 100 liter reactor. And then when we start working with the powder, the reactor, it was bought in China, the reactor, and then we start mixing the reactors. It works as an agglomerator. We didn't know that. We end up with balls of concentrate. Because we didn't know. So again, you need to feed, you need to change the pellet, because as engineers, we are not good in mixing. We are not good in mixing. That's the reason, because they ask you to review the 3 classes that we have with a company that supplies a mixer for lithium carbonate, also for autoclaves, because we are just like me. I have some criteria, some number, of course I know a lot of stuff, but mixing is something that we are missing in general in all the programs in engineering, and it's very, very important. So these guys are really good. I think we've been doing 4 seminars on that. Actually, this is an African, it's called Afromix. It's a company from South Africa. They do all the modeling. They did this year they did the CFD modeling, but it's not, I mean, I don't like CFD modeling, but it's all the way around. They start with an industry project, say, look what happened with the pairs. We're corroded, we're broken, simulate to determine what happened. So start with the problem. So in this case, I believe, okay? Again, don't believe because it's a European company, it's good. In the next page, we talk about what happened with Bolivia when they sent to Chile barrels of residuals material. And it's supposed to be stabilized by the Chilean company. So the Swedish guy said, your problem. This is no longer possible. And actually, in Chile, in the world, there is a regulation. When you take care, when you have a product, you are responsible until the end of the product, including packaging and stuff. For example, today we have called the law, it's called RED, remember? For final residuals, do you remember the law? Okay, for example, the tires producer for big trucks, Michelin, French company, is the RED. RED. It's responsibility and product responsibility. So you sell the tire and you need to take care of that. So what is happening with tires today, you cannot dispose anymore, mining tires. You sell it to another company, and there is a big company at Antofagasta, Caltire, that cut it and go through a process called pyrolysis. In the pyrolysis, you separate metal mesh, you end up with a carbon, a product. Very interesting, this carbon can be used for batteries. You purify the carbon batteries, and also generate an oil. We will be visiting a pilot plant in San Pedro de Gama, which is for pyrolysis. So why can't we have that? Because there is a law that doesn't allow to dispose the tire. So you're buying your country, whatever country, if you don't have a regulation to that, it's meaningless, you know what I mean, trying to develop a technology in that direction. So you need to seek policy, environmental restriction, and then develop technology. Unfortunately, it's like that. You know what I mean? Understand? Okay. And in this case, we have no regulations, so those are all the steps that happen. Still, it's under trial because many people got ill, and in this facility, this place, they have cadmium and lead, and they build houses. So it's a very bad impact to the people who live there. Okay, you're seeing the news. You don't need to read it, but that happened with again Swedish company. The first talking about environmental issues, all this stuff. Swedish company in Chile. Okay, it's a chain, really a chain. Okay, so some conclusions. There is no such a thing as sustainability. Whatever thing we do, we will have impact. Okay. Whatever thing we do, we make a whole without. What can we do now as a process engineer? Taking residuals and getting value from that and reducing the toxicity and reducing the harm of the products. But whatever we do will have an impact. Eolic plants, solar plants, photovoltaic, the big problem now is recycling. It's very difficult to recycle that. Lithium batteries, 5 years, they need to recycle. So we need to think reducing all the disposal, and the only way to be that is going to be possible is because you can add value. You can convert environmental problems in new problems. That is our goal. Okay. We cannot stop smelters. We cannot stop all the smelters that we have in Chile. Otherwise, we are vulnerable because we are selling concentrates. Imagine what happened in Congo. Congo is a very rich country, uranium, cobalt, but many companies are there. 80% of the companies are Chinese companies. Sorry, yes, Chinese companies. There are 20 companies. 80% is owned by China. Today, China produces 60% of cobalt. 60%, but they don't have it. It's in Congo. Okay. Okay, whatever thing we do, extract, concentrate, it depends on the characterization of the material, on the molecule, the mineral molecule. We can do whatever thing we want. There is no restriction. Uranium, thorium. If you want to go solvent, we will see that more in detail in the process design. If you see solvent extraction, you can extract neodymium, europium. If you want to characterize rare earth elements, neodymium, praseodymium, you can do it with ICP, TACE technology, and there are specific technology to extract. No limitations. Okay. The only restrictions are to have a cost-effective equipment. One of the problems is dealing with solid liquid, fine particles, with the solution, residual solution. Sulfate is a big problem, even mining company. Removing sulfate is a pain in the ass. Big one, big one, big one. We haven't solved that. Anglo-American today is accumulating gypsum, a lot, gypsum, which is very unstable because they have neutralization of acid solutions, and they're producing a huge deposit of gypsum. So sulfate is something that we don't have. We're really clear how to remove. Sulfate is a very good topic to study. Either membranes, not precipitation. Precipitation is also limited because you end up with a sludge that, let's say, the finer the particles, you will end up with a lot of water. You know what I mean? Fine particles, you will have capillary retention. When you have, for example, precipitation of arsenic, any fine particles, you end up with 90% water. So if you have a sludge with 90% water, fine particle, you cannot remove it. This is called capillary retention. You can use thermal process, you can use electro-osmotic dewatering, but this is a big issue. Generating sludge, generating sulfur, generating, because it's easy. When you have sulfur, you have acid solution, you add lime. That's it. But you solve this problem, but you end up with another problem. And then we need process engineering. Okay? We'll be seeing cases. Okay, that is a short assignment. I think we don't have the time to do it now, and I'm sorry to the assignment to. I talked at the beginning. We don't have problem of scarcity anymore. Water scarcity is not a big problem because if we have energy, it's solved. Today, the technology to produce a large scale water from seawater, it costs $1.2 a cubic meter. Big price, nothing. In terms of energy, today is 3.2 kilowatt hour per cubic meter. It's the energy consumption to take 2 cubic meters of seawater and produce 1 cubic meter of potable water. So a 50% recovery. You cannot get more. 50% recovery, 3.2 kilowatt hour. And again, talking about this readiness level, the reverse osmosis process at the beginning started with 20 kilowatt hour. And that was used in space missions. Russians developed electrodialysis, Americans developed osmosis, reverse osmosis. But for a space shuttle, 20 kilowatt hours is suitable. Then when I started with reverse osmosis, I worked for an American company, reverse osmosis, back to 1997, 1998. In this time, the commercial plants, the energy consumption was 6.5. Because they use the discharge, which is the brine, that it has a lot of pressure in turbines, Pelton turbines, and you recover energy. So from 20 we end up with 6.5. And now there is another technology that recovers this pressure, and now we have 3.2. On top of that, we are working, materials are working with different materials in order to reduce the pressure, and in theory, we can end up with 1 kilowatt hour per cubic meter. Thermodynamically speaking, to separate is 1 kilowatt, so we still have a gap. Okay? So reverse osmosis is the technology. So that was a small activity. I'm not sure if we cover, in process design, yes, we cover membranes. We'll see more detail on reverse osmosis. Okay? Any question at this moment? Yes. 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 Today is discharged directly to the sea, and depending on the current, in general, it's diluted, dispersed, but depends on the country. In the Middle East, need to discharge it very far away, kilometers. Here is 200 meters. Okay. But since you are working for many years, the plant worked for 30 years, you will end up with metals. You will end up with cadmium lead, and that's the problem. So what we should be doing is taking care of this solution, evaporating it and converting it. Why we don't do that in Chile? Because sodium chloride for us is not relevant. We have mines. We export sodium chloride to Canada for snow. Okay, so it's not commercial. We want once we wanted to extract magnesium, which is 3% magnesium. If you review critical, you know these critical elements, this risk of supply and cost. You know these costs. See. Okay, magnesium is just below the precious metals. You have critical elements, precious metals, and then you have magnesium. But in our case, we also have deposit with a lot of magnesium. Once we try to get lithium, but we have a lot of lithium. So it depends on the country. So what we should be doing is evaporating. We cannot use any more reverse osmosis. The limit is having 70%. Otherwise, you have it's called polarization of the membrane. And then you need to move to forward osmosis. It's a funny name because it's just osmosis. So they call it forward osmosis. It means you have saline water. We're talking about 70,000 microsiemens centimeter, the double of seawater. Membrane, reverse osmosis membrane, drain, flat. And then you put this solution in contact with water, ammonia. And this ammonia has 200, and then the osmosis occurs naturally. Okay, so you remove water from this discharge. Okay. And then since you have ammonia, you have a heat 40, 50 degrees, no more than this, you evaporate it. You remove the water. And you restore. Okay? That can be done. In our case, we are doing something different. Regarding the concentration, we are introducing hot air bubbles. And we will work on that. Hot air bubbles, because you evaporate that. And then whatever concentration you have, it will settle. We will see that. We have the device here. Okay. This is another pattern technology. It's called evaporation using hot air bubbles. Because you increase the vapor pressure. Okay? But yes, we need to be here. The problem is huge amount of water. There are plants that produce 1 million cubic meters per day. So you have 2 million cubic meters. And regarding ecosystem, nothing happens. You see more fish, even in the pipes. I think I showed some of the picture. The abduction pipes, when you suck the water, is full of shells, algae, big ones. Actually, it's a big one. They grow because it's kind of a little bit warmer. It's concentrated in nutrients, and we see. But in the long term, yes, it will be more. I'm talking about something that I didn't measure, but we do have a work there when they have divers that took samples and made the profile. They studied the current. We have these documents. They studied the current to see how this dispersed solution, radial dispersion, and different depth, and they measure a parameter which is PSU, practical salinity units, which is a normalized way to measure the conductivity based on potassium chloride at 20 degrees. You will see that. So we have those numbers. That was in Antofagasta, the largest for population, for human consumption, saline water plant. It's not that big, it's 450 liters per second, built in 2000. So we have 20 years experience. Okay. Okay, now I'm talking about healthy planet, but more Greenpeace stuff, but it's important to understand the concept. Let's go directly to 42. In short, you will see this diagram, what is happening now. We extract resources, we don't utilize the energy, we don't plan properly the urban planning. So what is the healthy planet? When you are moving to renewable, listen up, we have a lot of photovoltaic. A photovoltaic will generate receivables. Aeolic, it will generate problem with the blades. Today, Denmark, one of the largest aeolic producers, in the world. I'm not sure you've been in Denmark, because in the coast is plenty. Now they are working how to recycle the blades, because with the UV radiation, so you always will have a problem. Okay. If we talk about photovoltaic panels, it doesn't mean that you don't have CO2. You will have a footprint of CO2. If you put photovoltaic panels in your house, you need to wait 2 or 3 years, because to build this photovoltaic plant, it has a lot of CO2 materials. If you are in the city, it's kind of CO2 accumulated just for building it. You know? So it's 2-3 years to pay the CO2. So let's say in the year 3, you're not contaminating because you're using solar energy. You know what I mean? But if you do the same in a mountain when you are far away of the grid and you use diesel fuel, 3 months. Okay. Because the alternative is using fuel. Okay. Electrical car, yes, you reduce CO2, very good. But if your energy matrix is thermal with hydrocarbons, it's stupid, it's worse having electrical car. Because you are generating with CO2 footprint. Right? Okay, electrical car, very good. But the life expectancy of the battery is 5 years. What are you going to do with batteries? Battery has 50% carbon, 3% lithium. Do you know something? Water? Okay. No, the battery is around there. Okay. Sorry about that, I think okay, no, but I'm recording anyway. So, in short, our task is to convert residuals discharged from the rivers of process plant into product, metals, material, flue dust, tailing. Tailing is interesting, but it's complex because you need to put some water. So you need to choose a very special tailing. If you don't have roads, forget it, it's difficult to have roads. The best place to recycle tailings is when you have roads, you have access to water, I mean pipes, and people around. People around because you are fixing the problem that is living around. So you are stabilizing food. If you don't have the 3 parameters, don't waste time with the tailings. The only thing that you can do in massive scales is having a construction materials. Construction material is something. But we have a lot. Imagine Escondida produce 50 million tons per year. 50 million tons. Chile produce a big hill every 3 days. So it's too much amount of tailings. Imagine Escondida process 300,000 tons per day. 300,000. So, and you are extracting just less than 1%. I mean, the grade is 0.6, 0.5, you have 90% recovery. So you are extracting as usable material only 0.5%. The rest is tailing. And not to mention dump. I mean, when you mine, that mining, that it's a lot of that. So, talking about sustainable mining is not true. We will have always impact, okay? But we need to make it better. Okay? In food industry, in food, there is a lot of thing to. There is a lot of waste. This is different. Waste. Let's say one thing is when you lost a crop, for example, because of climate change, this is your loss. But wasting when you are on a cruise, you dump away the food. In Santa Maria, one of our colleagues work in the salmon industry. So in the salmon industry, you generate a lot of residual. A lot of residual go to the sea, and those contaminate a lot. You have a big problem. allow you to put pesticide, antibiotics in the fish. We're not sure if Norwegian, because I mean, if you have Norway and Chile, largest producers of salmon. So we're not sure if they did something in our water, I'm not kidding, because we use a lot of antibiotics. Yeah, we're competing a lot. Or anyway, so the thing I'm doing, my colleagues here, you have the fillet of salmon, and then you have the bone. The bone is roasted, it's grounded in a nanoparticle mill. You will see the nanoparticle mill. And then these nanoparticles, it's injected in the fillet. So you end up with a fillet enriched in calcium. You know, calcium is the mineral. It's a natural calcium that has better absorption. So they're working with the medical school, you know, so they're changing the quality of the product using a residual. They're doing that today. Okay. It's not our field, we are mineral processors, but just understand it, but it's something and put it back. The other thing they're doing is increasing the life expectancy of the products. So you have strawberry. Strawberry has only once its life expectancy is gone, you dispose the material. You have food. So they're using advanced drying process. They use lyophilization. When you cool down and use vacuum, and then to improve the quality, they use perforate lasers. Okay. Then you end up with a strawberry. You can keep it for 50 years. Okay. I'm not kidding. You will see. You will see. We have that. So this is another. I'm talking about food. There is a lot of technology. I just was talking with one of my colleagues, which, by the way, is the director of the graduate program of PhD and master. And by the way, we will have on 29th of August the formal reception of all our master students. You are not only Erasmus, you are chemical engineering master program. As a whole, it will be a ceremony on Tuesday 29th. So we're talking yesterday when we have this lyophilization process in vacuum. They also use plasma. They're studying using radio frequency to generate plasma to kill all the bacteria. So you know, it's very high tech. Plasma, we use it to recover materials. You know, to recover materials, pipes. So they are integrating a lot of technology in the food. In our case, we haven't changed that much, but a lot in materials, membrane, in resins. There is a lot of developments. Yeah, so, I mean, we can make it. Yes, we can make it. Today, you can extract lithium directly from the solution. You don't need to evaporate. We are rich, Bolivia, Chile, and Argentina is rich because we have 0.6% lithium brines. You just put it on carpets, evaporate for 12, 18 months, but you lose a lot of water in the most arid zone of the planet. But they say, okay, by the way, this brine is not water. It's not considered by law, it's not considered water. First thing, law, it's not considered water. It's brine. And secondly, because of the water cycle, it comes back. So you can debate that. I don't think it can be done. But today, there is direct extraction. This company in Argentina, a now buying company, is doing the direct extraction of lithium without evaporation. Okay. So it's a lot of going on in technologies to make it sustainable. And then if you go to, that is called incremental improvement. Let's say we are taking the bones from the salmon, re-injected, nothing to do with climate change, just to that, insulation, just to make you think. Do you know what is a heat pipe? Heat pipe. If you don't, it doesn't matter. You will feel it. You will never forget what it is. It's a heat exchanger that can recover energy. Most of the losses are when you have waste energy. For example, even your chimney in your house. If you have a chimney in your house, you can recover this energy. And also, we can use Heat pipe with 2 degrees difference, you can recover energy. You can cool down. But I will not tell you more. But your computer has a heat pipe inside. Okay? Then we have Peltier. I have all these toys in my office, by the way. And then you have Peltier cells. This Peltier cell converts direct thermal energy in electricity. Direct. Sorry?
It is not exactly like a cycle using the temperature or
This one can remove very efficiently heat. Evaporation, condensation. You will see it. I have the devices. You will feel it. With the thermal camera, you will see it, the temperature. Peltier is something different. It's a plate, it's a specific equipment where you can take 40, 80 degrees and convert from thermal energy directly to electricity. Like magic. I have a toy in my office, you will see. What can be today around 5, 5:30. Just to see, to demonstrate how can I generate magic from hot water. How can I generate electricity from hot water? Okay? So what I'm trying to say, science is going in one direction, and there is a lot of stuff, but we need to integrate. For a large scale of energy, I'm talking about, it's called low enthalpy. I'm talking about 100, 120 degrees. Eduardo, steam power plant, it works what temperature? 150. How much? The temperature. You're working on that. Next time, you need to work. She's specialized in thermodynamics, working in Aspen High-Seas. Let's say Brighton cycle, you end up 65% efficiency, no more than this. Remember, the thermal efficiency for thermal processes, they have no low. We will have the hot temperature, low temperature or hot temperature, 1 minus lowest temperature, hot temperature, yes, our reference. But we have 65%. Not that good. So when we have 100, we dispose 100, 120, and then we got to go over that. But for those cases, we use different cycles. We don't use water, we use organic cycle. Okay? I think I moved to thermal energy. Saying it's not only renewable energy. One of the highest waste is thermal energy. We waste a lot of thermal energy. We need to integrate, but it's more process design. Okay? We recover a lot of energy just connecting a heat and pressure exchanger. A lot of energy. We don't need to go we don't need to go everything renewable. Okay? Thermal energy is something that we now recover a lot. Not to mention insulation, houses insulation. You are suffering that today in Chile. Because temperature is not that cold, it's not -10. So our houses are fully insulated. You're suffering that. Okay? Okay, I'm gonna end up because I want to put my hands on, end up. So all this integration, one thing is residual, but another company can take it. We call it industrial ecosystem. Industrial ecosystem. The good book on that is this book. Unfortunately, I don't have the reference here. This person is, I forgot the name, she's a chemical engineer from McGill University. Now she is professor in Concordia University in Montreal. And she has this book. I can give you the PDF format. So just to understand, in order to reduce all this, I'm in the page 46. Whatever residuals you generate, someone else can take it and create a company. This is ecosystem. Denmark has very good examples of that. And if you reduce transportation with raw materials, for example, our president wants to build car batteries in Chile because we have lithium. This is a very stupid idea. because car battery has 3%. What could be the model? Okay, you have lithium here, it's near. But you need cobalt, you need nickel, you need carbon, you need to assemble, you need other materials, you need to bring overseas different raw materials, put it together, build the battery, and then send back the battery to Europe in the assembly line for cars for US. Okay, so the idea here, it has two strong ideas. One is whatever residual that you generate can be converted to something else. The bones example of the fishes, of the salmon, okay, whatever. And when you assemble things, you need to think carefully. You cannot build car batteries because the CO2 footprint for that is going to be a lot longer, a lot higher, because you don't have all the materials. So you need to reduce transport. Transportation is one of the big issues. What are we doing stupidly here in Chile? First, lithium production. Lithium production today in Chile, the efficiency is 30–40%. Because the law, lithium is owned by the government. So they have royalty for different companies, and the limits are in the amount of lithium carbonate that you can produce. So this is taxed by the amount, but not the efficiency. With 30–40% efficiency. The rest is waste. So first, you use evaporation. We're losing water. I'm talking about a lot. If you see by Google, you see the ponds are big. It's big one, 500,000 square meters, one pond. They are evaporating about 500 liters per second. We measure with Google, measure the square meter. Okay. This evaporation concentrates from 0.6 to 6%. And then this saline brine, 6%, is transported by trucks from a desert, Altiplano, to near the coast, La Lena, 200 kilometers, 250 kilometers. Okay? Process. You end up with another brine solution. It's very, very concentrated, can be 600, 900 grams per liter. It's like a honey, it's like an oil. The plant is increasing, so you no longer can dispose on ponds the solution. What are we doing? Taking back the solution and truck to the field. Okay, what do we need there? Technology to increase evaporation, produce crystal, and recover the water. This is the technology that I'm presenting in the Las Vegas conference, recycling next week. Next week, it will be Tuesday, I will not be here. I'm presenting this technology for recovering water from really saline. So we are in the stream of innovation and technology to tackle the problem that you're looking at. Okay? And the good thing, you will have more details. I cannot deliver. It's also a patent technology. I will not show the reactor, but you will know the reactor because you are my close. Okay? And this reactor, I will tell you, is a loop reactor. Two columns connected, I inject air in one, generate gas holdup, exchange the density, and start moving along. This is the reactor for hot bubbles, but the same reactor is the invention for leaching bad particles. Got it? Think about it. Okay, I have a meeting. Remember, block 3 and 4, I sent an email. It will be done 5:30 soon after dinner class. Sorry about that, but we are very little time. So, and you understood that? You have class with Luis Binet? Okay, again. The next block, we will not have class. We will have class blocks 5 and 6, sustainable engineering. Okay, sorry, process design. Then block 7 and 8 will be sustainable engineering. This class. But the time I have 3, 4, which is process design, I'm moving it to 5:30 because I don't have more time. Okay, also, I can come tomorrow about 9, 10. it's holiday, but I don't have problem because I'm traveling tomorrow tonight. Okay? But I don't want to lose any, I don't want to waste any class. So there is no stuff to learn. Okay? So you have the first assignment. Of course you can